Okay, well, let's pick up with resonance. Resonance is a big topic. I cannot tell you every single thing about resonance here in lecture. You have to be working with it. Hopefully you've been working with it along the way. I mentioned it several times. We had resonance with acid-base chemistry way back during the first week or two. I suggest you pull out the acid-base handout with the resonance there. Okay? And I introduced it in sort of a certain way then. We're doing a deeper intro here now. Okay, this first page is actually a lot of theory. It can be a little bit tough to get the workings of it, but it's worth doing. The next page we'll start, okay, this is what we do in resonance. Let's continue with some of the theory here. And we also have a divide between, last time we talked about it, tests and everything, so we're kind of not, the discussion is not fresh. I'm going to do enough on this first page to get us through it. When we get to the next page, let's say, okay guys, let's do resonance. Over here, maybe resonance structures. All right. And there's two things, knowing the theory and also just knowing how to draw resonance structures. And let's look at that. Drawing resonance structures. You only want to move what type of electrons? Okay, good. You got a list of golden rules back there, yeah? All right. We got pi electrons here. Because you ain't got pi electrons, you ain't got no resonance. Right? I can move these. What if I take these two? And you can move them any way you want. Now, once we have polarity, you want to move them according to polarity, like towards an electronegative atom. There's really no polarity here. So that sort of hurts us, and it reduces the sort of the intuition. But still, okay, I'm going to do it here. What if I take these pi bonds, just move these pi electrons over to the carbon? That is, instead of bonding electrons, let's move them back to the carbon as a... Yes, so what does that electron movement give? It's sort of a mechanism there. I'm moving electrons here. Okay? Now what's on this carbon? Did we do this last time?
Yes.
We have, okay, we ended here, one pair here. There you go.
No. Charges.
Right, okay, good. There you go in terms of what this arrow gives, but also now charges. And if you do charges, that's a minus, but this is a plus. And yeah, we did this, and we said all resonance structures have the same net charge. Net neutral, net neutral. Okay, that's the second golden rule. Second one we mentioned. I don't know if it's number 2 on the list. Okay. Of course, you got to know there's H's here. How many H's here?
1.
1. You knew this week 1 of the course. Okay, 1 H there. There's still 1 H there. So how many bonds does that carbon make? 3. That's why it's a positive charge. Okay, so you got to know where your H's are at. There you go. All we move. Are these two the same structure? No, obviously they're different. Different structures. Not different compound. Okay. Same compound. All right, which structure is best? On week 1, if we had drawn a resonance structure of a Lewis structure of this compound, would you rather prefer that or this? This. This is the best resonance structure. Why? Because there's no charge separation. Separating the charge is a higher energy. Okay, we can draw another resonance structure. Did we draw a third one last time? Yeah?
Yes.
Windshield wiper. And now we have charges. And now we have some more intuition. On the next page, we'll start with charges. I like to say, well, how do you stabilize a positive charge?
With a negative.
Move electrons towards it. I can move these electrons back. That would just give me this structure back. What if instead I move this pi bond over here? Now that's the old windshield wiper. I move this pi bond over there like that. Okay? What does that arrow movement give? Well, we didn't do anything over here, so that's all the same. There. What's here now? It's missing a bond. It's a positive charge. Same net charge. These are all resonance structures. Still, which one's best? The original's best. What's the consequence of this? The The true structure, when you talk about resonance structures, is really a blend of all resonance structures. And we'll do that real quick. Again, to get the full step-by-step theoretical discussion, it would take us 2 hours. We just can't do that. So I'm going to do bits and pieces. And the piece I'm going to do right now is talk about the hybrid. The hybrid is a blend of those there. Ultimately, you have the core backbone. And then we can talk about this. We have enough resonance structures up here. We may could draw additional ones. I'm not going to do that in this example. Let's talk about blending these. And the way we do that is, look at the bonds here. Between these 2 carbons, there's double bond, but here it shows single bond. What's the average of double, single?
1.3. It's closer to 2 than 1.
Now, when we ask that, we don't actually like put it on a calculator and do an exact average. We typically just stick to sort of half. And say this, the bonding between these 2, it's not a double, it's got some double, but it also has single. What's sort of halfway between double and single? What's halfway between 1 and 2? 1.5. Okay? Now, yeah, there's a little more double bond character than single bond character, so it's a little more than 1.5. But we typically just say about 1.5, and it's probably written there. So it's not a double, it's not a single, it's somewhere in between. How about that? And this is kind of how he shows it's not a double, it's not a single, but it's sort of 1.5, 1 and some more. But it's not completely 2. Well, how many bonds between the central 2 carbons? Single bond, oh, double bond character. So what's between single and double? 1.5 in general, approximately. Okay, last 2 carbons, double, single. So is it single or double, or is it somewhere in between? Somewhere in between. And somewhere in between, we're doing it like this. And this becomes more of the true structure here. And I'm not going to do this is your resonance hybrid. And the electrons are really spread out all through here. Ultimately, why? Because if you go back to the orbital view, don't we have 4 p orbitals? 1 electron in each. There it is. Why just say these are overlapping and these are overlapping? That looks like 2 isolated pi bonds. Well, guess what? The central 2 are also overlapping. And the electrons are really all spread out between those 4 p orbitals. That doesn't look like it's all spread out. It looks like there are 2 here and 2 there. Does this look more like it's all spread out between the 4? Yeah. See, if you could look at this compound, the electron density would look more like this. Whenever you do resonance, you can draw more than one structure. But once you're able to draw more than one structure, your structures actually would become fake. None of them are actually no longer accurate. The accurate structure is actually becomes the blend. Okay? It's like colors. If I told you the color was red, it's red. That's it. What if I told you the color was a mixture of red and white? Is it still red? Is it white? It's actually no longer either, because the mixture of red and white is pink. So once I told you red and white, actually neither one of them is no longer correct. Okay? The structure's not red, white, or blue. It's a blend of all that. Problem is, drawing a pink structure is difficult. It's like, where are the electrons? How do I work with this? And so I just tell you, hey guys, it's red and white. Do you understand what the blend looks like? Again, we'll do this more and more. There's some little theory below. Bond order. Bond order is just saying how many bonds are there. Okay? And so is the bond order between these 2 carbons 1, 2, or in between? In between. Is it exactly 1.5? No, not in this example, because the double bond appears to contribute more than the single bond. Think about that. We'll come back to that. You got to think about the theory. But you got to know where p orbitals are at, and how many electrons are in your system. Okay. Dealing with charged species, things are a little much easier to kind of nail down. Ultimately, one of the things that resonance does for us is stabilizing charges. Very big in stabilizing charges. Let's look at stabilizing positive charges. This is a simple molecule. You'll see a structure that's in many different systems. It's called an allylic cation. It's when you have a carbocation next to an alkene. Okay. And this cation, it looks like a primary carbocation. And primary carbocation is typically bad, right? Okay. Tertiary is best. Secondary okay. Primary kind of bad. Right? But there's much more here. This is resonance stabilized. Again, we can first talk about theory. We can then just do resonance structures. Actually, let's just do resonance structures first, then talk about theory. Okay. You just move pi electrons. Here's an important question. How do you stabilize a positive charge? Do you move electrons towards it or away?
Towards it.
Towards it. Okay. Just start with that number. Something that's missing electrons, once electrons move towards it. Can we move electrons towards it? Yes. In this case, the old windshield wiper. What if we just take this pi bond and move it over here? Like this. What does that give? The double bond is now here. What's on this carbon now? Positive. Now the positive charge is there because there's two H's there. It's missing a bond. Okay. That's a resonance structure. Okay. Can you draw any other resonance structure? No, it's just too simple. That's all we have here. I can windshield wiper these back. I can just come this way. By the way, double-headed resonance arrow. Maybe you move to another resonance structure, you show this double-headed arrow. It's not an equilibrium arrow. Resonance arrow. Appropriate use of arrows, including mechanism arrows, but also this type of progression arrows.
Dr. Stevens?
Yeah.
Would you be able to move the double bond to create a little pair in this thing?
Theoretically, you could. You want to just do this. Okay. I'm going to do that, but I'm not going to erase it because it's going to be bad. But theoretically, you can. What would that move give? We didn't do anything here. The long pair here. And what's here?
Positive charge.
Yes, that would give that. That is a resonance structure because all we did is move pi electrons.
Why could you not move the double bond from the secondary carbon, the middle carbon, like so it forms like a triangle instead? Can you make a bond from like the first to the last carbon?
Something like that? No, that's going to...
No, not from there. So like the two ends would connect. So the middle one would be a carbocation.
Just turn it into a ring.
Yeah, into a ring. A
Oh,
triangle.
you mean move these away from that carbon?
Yes.
Here?
And then go across.
Like that?
Because would that not be more favorable with a secondary carbocation?
Okay. Because that's not resonance.
It's not resonance.
That's a carbocation rearrangement.
Oh, we're not moving a double bond.
Because what type of bond did you just make?
A single.
Or what type?
It's a single.
Sigma. You turned your electrons into sigma electrons. Okay. That is a different compound. And when we do resonance, we're not making different compounds. It's the same compound. We're just showing a true representation of that one compound. Okay? I mean, how many compounds do I have drawn on the board between there, and there? One. This is one compound we're dealing with. Just like pink is one color. Pink comes from red and white. So is pink 2 colors? No, it was 1 color. What if he makes 10 colors and got a new color? Is a new color 10 colors? No, the new color is it's 1 color that came from 10. Okay. Resonance structures are all just different forms of one compound. It's different fake forms. They're all blended to give that one compound. Okay? All right, back over here. I drew that, but I'm going to quickly erase it because it kind of convolutes the discussion. But right here, which is major? Which is the worst? Let's not do major, let's minor. Which is the worst? Of 3, which is the worst? The one we generated over there, because now we have 3 charges. Okay? It's theoretically a resonance structure, but it's pretty darn bad. Okay? And so, what we're ultimately looking to do in this example is stabilize this thing. We didn't stabilize it by doing that. So I'm not even going to consider this resonance structure. All right, good question. Let's just do this. And let's get rid of this here. Do that. These 2. There's no other resonance structure. No other good. And sometimes my questions will say, draw resonance structures that are equal or better than this one shown, or something. Or draw resonance structures that show delocalization of the charge. And then you could say, well, I could draw that resonance structure, and then I would say, yeah, you can, but it doesn't show delocalization of the charge. So you didn't really stick with the directions. All right? So of those 2, which is the best? These are equal. These are equal contributors. And so this is where we can really talk about the hybrid and get more precise. Those are equal. Between the first 2 carbons, is it single bond or double bond? It's exactly 1.5. 1.5. Between the other 2 carbons, is it double or single? Is it 2 or 1? It's exactly 1.5 because these are equal blend. Okay? There we go. Charge. Okay? See, again, this is much better, easier to do these things. Is the N carbon positive or neutral? Positive 1 or 0, neutral?
Partial positive.
It's right in between. It's a half a charge. Now, we don't really say that. We just say partial plus. This carbon, neutral. There's never any charge there. How about the other N carbon? Is it neutral or positive?
Partial positive.
Partial plus. A perfect blend. And that's the hybrid. This is red and white. What's the true structure? Pink. Okay? That is, okay, let me ask this. Then we'll go back and do a little theory. Which bond is longer? This bond on the left or right? Which carbon-carbon interatomic distance is longer?
Left.
Left or right?
They're the same.
For this molecule, which carbon-carbon bond is longer? For this molecule, both carbon-carbon bonds are the same exact length. Because for this molecule, here's the structure of this molecule. Which bond is longer? What's the bond order for over here?
1.5.
1.5. What's the bond order over here? Isn't that what we said when we drew this? It's exactly between 1 and 2. We have a very precise bond order now. Okay? Bond order equates to really bond length. It's the amount of bond there. Okay? In this molecule, the 2 carbon-carbon bonds are the same exact length. Why were you looking at this structure? It's fake. That one's fake. The true structure is your hybrid. If you can look at this molecule, it's the electron density here is spread out through here, very symmetrical. The charge, if you could have like colors for charge, these 2 would be both the same color there. Okay? The charge is delocalized. Delocalization. The charge doesn't just sit on the N carbon. this charge is really spread out onto both of the end carbon. Now we say separation of charges. Not good. That's if you're going from total no charge to some charge. This is actually good because instead of all the charge being on one carbon, we're spreading the charge out. It's the same amount of charge, we're spreading it all out. Okay? It's just like force. Would you rather be put all force right into one spot or spread the force out? Yeah, if an elevator is plummeting down, you should lay down. That way when you hit the ground, the force will be spread over your whole body. Okay? When you hit. And that'll be better than if you're just standing there. Because if you're just standing there, all the force is going to be put into your feet, you're going to break. Okay? You'd rather spread the force out. You'd rather spread the charge out. Okay? So what?
How do you know that?
Well, you know a lot of things I don't know too. You know there's a lab coat somewhere. It's just, okay, is that right? Spread the force out. Okay? Spreading the charge out is better. So we've delocalized the charge, and that's the power of resonance. Very often we don't even draw the hydrate. That's the theory. We can get deeper into the theory. Let's go back to p orbitals. Don't you see two p orbitals here? One electron each, that's pi bond. Yeah? Does this carbon have a p orbital? Yes, it's sp2 with an empty p orbital. Okay? Well, guess what? Are these two p orbitals interacting? Yes, they are. And at this point, you have three p orbitals conjugated. How many electrons in the pi system? 2 pi electrons. 1, 2. That one was empty, right? 2 pi electrons. We have a system here of 2 pi electrons spread over 3 p orbitals. Okay? And this becomes like a garden hose. If you put 2 quarts of water into a garden hose, is the water going to spread out into the garden hose equally? Yeah. And that's ultimately what happened. The electrons are spread out in there equally. Is there anything on the board that kind of shows that, how they're spread out there equally? Yeah, the hybrid, the true structure on the end over there. Okay? So this is more than theory. That right here is us drawing resonance structures on a paper, and that's ultimately one thing we got to be able to do, is draw these fake structures. But you got to understand the theory that's here too. Okay, it's called a benzylic cation. Can you draw resonance structures of it? How do you stabilize a cation? Move electrons towards it. Okay. Is there any method of moving electrons towards it that we mentioned? I actually gave it a name. I called it the windshield wiper. Okay. We'll do other kind of movements. What if I take this pi bond, move it here? Yeah? Will that give us another structure? Does that give that? Yeah? That is a resonance structure. And you see how we've delocalized the charge? We're moving the charge around. And guess what? At this point, neither structure is correct. It's now becomes a blend. And in the blend, is all the charge sitting on that carbon? Or is some of the charge on this carbon? Yes. And you just know that. You don't always have to draw the blend. At this point, we see the charge is going to be placed around on different places in the blend. But here, can you draw additional resonance structures?
Yeah.
Yeah. What if we windshield wiper this up? Yeah? Positive here. Delocalize the charge to that carbon. Any other resonance structure that we haven't drawn yet? Don't worry about it. See, if I try to stick them together, it gets up. Yeah? What if the windshield wiper just over here? You now have, everything comes from the error movement, right? Everything else is the same. What did we do differently? That's now over there, right? And what's here? Okay. Any other? We could put this down here, which will whacker that down. What would that give? Mostly the same. The charge gets back to the same position, but is it exactly the same? Charge gets back to the same. But is that the same as we started with? You see how the three pi bonds in the ring are in different positions? Not exactly the same. But I would not probably show that. Charlie Brown on the back or Dennis the Menace sort of gets at that. Okay? You can move these around here. I'll do that. What if I move these up, move these here, and move these there? What does that get? Then that gets over here. That's the benzene resonance. But see, if the question asks, show resonance structures that delocalize this charge, what's delocalized there, it's delocalized there, it's delocalized there. Showing that it's not delocalized, it's back to the same place. So my directions would keep us from having to show that. But it is a resonance structure. Everything comes from the error removed. So what's a true structure look like? A blend of all those fake ones. The true structure is going to look like like that. Because what's the bond order between that carbon? That's called the benzylic carbon. A cation next to a benzene ring, carbon next to a benzene ring is called benzylic. It's resonance stabilized. It's very resonance stabilized. That carbon is also called the benzylic carbon. What's the bond order between the benzylic carbon and the ring carbon? Is it 1 or is it 2? Now it looks like it looks like closer to 2. But we're not going to do anything. We're just going to do 1 and more. But it's not fully 2. Because right there we see less than 2. Okay? Any of these. Let's look at these 2 carbons. I showed 1.5. 1 and some more. Okay? Well, that's just 1. That's just 1. That's just 1. Ah, but look right there. More than 1. So since it's more than 1, I have 1 and some more. And you can do that all the way around. You're going to get 1 and more all the way around, and that's what we have here. Okay? Now, I kind of made that circular. There we go. Guess what? That carbon does not have a p orbital. So there's no resonance out there. All right? Every one of these carbons has a p orbital. Charge. What charge is on this carbon in the hybrid? Is it positive or neutral? What's blend of positive and neutral? Partial positive. How about this carbon here? Careful. Did that carbon did we ever show it positive? No. But guess what? We showed that one positive some. Those 3 were shown positive at some point. This is our blend. You can look at this cation. It really looks like this. And the charge is not sitting on just one carbon. It's really spread over 4 different carbons. Okay? So if you had a color that indicated lack of electron density, you would see lack of electron density at these 4 positions. You can really see the molecule. Okay? It's pi bonding. It's this blended bonding. Because all these p orbitals are connected, and once they're all connected, the electrons spread out all through there. All right? Just have to keep saying these things over and over, and you kind of eventually get the full story. Very delocalized. And the more you can delocalize your charge, the better. So which is more stable? Yeah, more charge delocalization here. What if I just drew this, though? Which of these is more stable? That one, because we can delocalize a charge. Can you delocalize this charge? That's an empty p orbital. There's one. Where's any other p orbital at? There is none. That's an isolated p orbital. You can't do anything with it. See, this has, how many p orbitals are conjugated here? How many p orbitals in your system here? 7, right? Every ring carbon has a p orbital, and that has a p orbital. 7. The electrons are spread out over those 7 p orbitals. There's no place to spread that out. You can't get resonance there. There's no conjugation. You can here. We showed one delocalization, much more delocalization here. Benzylic. You can also stabilize a positive by a lone pair. Was there a question?
So when you go back up to the resonance structures for the allylic cation and the benzylic cation, the resonance structure for the allylic cation, wouldn't that be the exact same structure as the one we're given? Because it's a propene, and you're never going to have a 2 propene, it's always going to be 1 propene. Whereas for the benzylic cation, you have visibly like different structures depending on where your double bond is.
Yeah, we had several fake structures.
Yeah.
There we had 2 fake structures.
Well, but I'm saying, wouldn't they be the exact same structure?
They have, well, they're not the exact same structure, but they do have exact identical ranges. And that's what got me so excited about that. I said, hey, it was a perfect blend.
Okay.
And that way, it wasn't 1, it wasn't 2. What's the perfect average of 1 and 2? 1.5. Okay. See, I didn't do that, talk about that down here because it's not as clean, because it's not a perfect blend. You all, how many did we draw down here? 5 or 6? Were they all equal, exact equal contributors? No. Of those down here, which one was best? We didn't say that because it's not as clean of a discussion, but we could have. Between this one and the other ones I drew, which one is best? Or are they all the same? The answer is the original one's the best. And the reason is if you can maintain that magical benzene ring that looks like the same benzene ring, it's got magic to it. You'll learn organic 2. So the original to me is the best. And so the structure is going to look not a perfect blend. It will look a little bit more like this because that's the best. And so in terms of charge, it's not equal charge on all 4 places. There's actually more positive on which carbon? That one. There's actually a little bit more positive there because of the things that contribute to that, which one is kind of better and thus is going to contribute more? That one. And if that one contributes more, you're going to get more positive on that benzylic carbon. Okay? That's what your major contributor is. A major contributor. It's contributing to the hybrid. Okay? Alright. That's basically, these electrons don't have to just sit equally distributed. There could be some reason that makes them sort of push towards one of those. Okay? And that's it. It's major. We'll do more of it. But up there, they were equal, so it was a perfect blend. Okay? Most of what I say is not going to answer all your questions. It should lead to questions. It should lead to questions. Then you go read, and you say, oh, okay. And then you ask. Okay, everybody understand all that? We're not here to answer all your questions. We're here to stimulate your thinking. All right? Another way to stabilize a lone pair, move electrons towards it, but we can also move lone pairs towards it. Okay? And what we can do is just take this lone pair and say, hey, oxygen, can we share? We can also let physics take over because electrons are minus. If you've got a plus next door, aren't they going to be attracted to it? I think I learned that in physics. Okay? These electrons will be attracted. What if they attract so much they move in and start sharing to make a covalent bond? We can show that. What would that look like?
A double bond and out.
Yeah. The lone pair is not moving over to that carbon. This arrow is the lone pair is moving in to make pi bond. How many lone pairs left on oxygen? One, because the other one moved in to make pi bond. Charge now.
Positive.
If this is positive, that should be positive, right? Where's the positive? Oxygen. Okay? That is a resonance structure. All we moved is pi electrons. Are these pi electrons? Let's start with theory. Well, we got an empty p orbital. Okay? No electron there. It's sp2, an empty p orbital. Okay? And by the way, we covered that during week 1. So if you're not up on what I just said, you need to go back and review. Graph the hybridization. Okay? So, what's the hybridization of the oxygen next door? Well, I think I've said this. Anytime a lone pair is next to a p orbital, it's going to want to be in a p orbital. Okay. Well, there's a p orbital next door, so one of the lone pairs is in a p orbital, right? And then the other one's in a hybrid. And it's going to sit off like this, and you see the 3 lines? 3 lines are supposed to be trigonal planar because the oxygen is sp2 trigonal planar. With a p orbital, one lone pair is in a p orbital. Why? So we can interact next door. And that's called resonance or conjugation. And so now we have 2 p orbitals. So if it interacts next door, is that a bond? Well, this is showing it fully interacting next door. So why didn't we just show that to begin with? Because at this point we have multiple structures, neutral structures, and blends. That is, how much is this interacting next door? You remember the pinky bond? Positive charge, right? We got a single bond, and then you're a cation, I'm a lone pair. Am I going to want to come over here and try to bond? Yeah, but I'm oxygen. I don't want to give up my electrons, so I'm going to come over here and make a pinky bond. Okay? Because I'm greedy. I don't want to fully give him my electrons. So we got a bond and a half. Okay? That shows a full double bond. This shows no bond. What's the true structure? Blend of these. And the true structure is it a single or double between the O and carbon? It's like 1.5. What about charge? Is the carbon positive or neutral?
Partial positive.
Partial positive. Oxygen, is it positive or neutral?
Partial positive.
Partial positive. And there's what your true structure really looks like. That's your resonance hybrid. If you could look at it, it would really look like that. You see the pinky bond? Okay, we talked about that a couple of weeks ago, yeah? But again, that's hard to draw. We draw fake structures and say, hey guys, this is red and white, the true structure is pink. But we can ask this, are these equal contributors? Do they have the same energy? No, they don't. Which one is a major? Which one's better? Who says this is better? Who says this is better? Yes, this is better. This is major. Major contributor, minor contributor. What does that mean? This structure contributes more to the hybrid. So, back over here. I call these both partial positives, but actually one of them is more positive. Which one's more positive?
Oxygen.
I told you that's a major contributor, so that means the oxygen is more positive. If this contributes more, that means you're going to have more positive here than there. Okay?
Why is that? Because oxygen
Good.
needs to have 2 bonds and 2 lone pairs, and it's greedy for electrons. So why would that be the major where it has less electron densities?
Okay, you made a pretty good argument. It just turns out it's wrong. And we mentioned that before. Okay. Why ultimately is this right? This is because it's got more bonds. If you count up total number of bonds, what did we do when we moved that in? We made an additional bond. And typically bonding is a good thing. Okay? Here's another reason. All atoms have octet. See, even though oxygen is positive, it has an octet. 2, 4, 6, 8. And if you look at the golden rule page, it discusses this. A greedy heteroatom doesn't mind sharing and taking on a positive, as long as it maintains its octet. If you ever do this and it doesn't have an octet, you will make the oxygen quite bad, and it will come looking for you and knocking on your door and saying, I want my electrons back. Okay? Read the golden rule page. Okay? The argument over here is, this looks better because we don't put charge on the oxygen. Actually, this is better for these two reasons.
What does that note mean, though? It says it's not stabilized by a CO or CN pi bond.
Where
Isn't
does it
that
say
what
that?
you're making?
I didn't hear you.
What does the note mean when it says cations are not stabilized by a CO or CN pi bond? Like, didn't you just make a pi bond to stabilize that, or no?
No, I stabilized this charge with an oxygen lone pair.
Right.
I think we'll do that a little bit later.
Okay.
Okay. This is a case where the hybrid is not a perfect blend. This is, we can talk maybe about childs from parents, okay? You ever see a kid that says, wow, that kid looks just like his mom and nothing like his dad? Okay? That means the mom was the major contributor to the DNA of the child, okay? All right? And the dad apparently didn't contribute much to the DNA, okay? All right? But sometimes you get a child and like, wow, that child looks half like you and half like you. Like a perfect blend of parents. That would be where the parents were like equal contributors. Okay? This is not equal. The child looks more like which one of these? The child looks more like the major one. So in terms of charge, there's more charge on oxygen. In terms of bonding between O and C, is it really pushing towards double or more towards single? It's a lot. Again, to assess your hybrid, look at your major and resonance structure. It's going to look more. That doesn't mean it doesn't look like this. Some. I mean, you can see some of the dad in the kid. It's like, if you look hard, you can tell. Okay. But you can clearly tell the kid looks like mom. All right? You see what I'm saying? That's this another analogy. Can you draw resonance structures here? Here you can draw more than one additional. Can you draw all possible resonance structures to delocalize that charge? I'm going to go ahead and move along. We got a long pair here. How about if I move these in, yeah?
Yeah.
Yeah? And that's the A arrow going that way. Can I do something else though?
Yeah. Make it to the windshield.
Windshield wiper, yes. How about that? B arrow. Yeah? Two. That's, in total, that's 3 resonance structures. Because the original one at this point is 1, 2. 3 resonance structures here. Can I draw another one? I'm not going to do that. I'm not going to polarize this and get three charges. Theoretically, we could. If I did that, though, would it move this charge? If I start doing something there and leave that charge here, I'm not doing, well, it doesn't say, I'm not delocalizing the charge. That's one thing we usually will have to kind of make sure we're doing. Okay, of the 3 here, which one's major?
A. Or all they're all the same. A.
Major?
A.
This one here is major. Could you draw the hybrid, where everything is blended? Okay, try to do that. Once you get to the hybrid, does it look like one of these kind of more than the other? The major. Let me ask you this. If if you were asked to show this cation, you could show it as a hybrid, and someone might look at you weird, like, why do you want to draw a hybrid? You could say, well, that's theoretically what it is, right? Well, but let's draw these sort of official Lewis structures, because that's how organic chemistry is done. Which of these three would you show it as a structure? If you were asked to just draw one structure, which one would you draw? I would draw the major one. Okay? So why did I start with that one? I didn't start with any of them. They're all fake. But it could be that this cation would be presented to you like this. Okay? How many different compounds on the board here? How many different compounds here?
It's one.
That's one compound shown 3 different fake ways. It's your structure, that compound is a blend. Okay? I'm not going to do the same discussion on all examples. Regiochemistry of reactions. If you react this alkene with HBr, which product would you get over here? The question is really, where are you going to make carbocation? Top or bottom? They would both be secondary. Is there any reason to make one cation over the other?
Stabilization.
Well, this is what I would do if you, to really show it out. Show both possible cations they could form when the alkene reacts with the H+. Show both possible ones and then say, okay, which one is better? And guess what? If one is stabilized by resonance, it's going to be better than one that is not. Okay? And really the answer here is what cation? Because if you form cation down here, bromine's going to attack there. If you form cation up there, okay? So this is a case where you can evaluate your possible cations, not just saying secondary versus tertiary, but maybe resonance versus no resonance. Because resonance does what to the charge? It delocalizes it. And delocalization makes it more stable. And so a delocalized cation is going to be better than a non-delocalized cation. Okay? Same thing down here. Okay? We don't react benzene and organic 1. Here's your alkene. Where are you going to make cation at? Right or left? They're both secondary. But do you see something else that's going to help cations? Again, draw both cations and look at them. All right? You got to do this. Draw both possible cations and protonate. We have talked about protonate and alkene with H+. Yeah?
Yeah.
For the past month? So hopefully you can do that. That's all I'm asking you to do. Look at the cations. And you might look for resonance. Okay? Please try those. We're going to move ahead. This is a lot of, I get bogged down here. Okay? But resonance is hugely important. At some point we're going to have to move ahead. You really got to come on Monday with questions and have done some of this stuff. Because I will start moving ahead on Monday. We did cations today. Next, anions. Please have looked at that though, because I'm going to move through it. It's the same talking points. See some of you in lab this afternoon, guys.